This talk is sponsored by the Central Virginia node of the Commonwealth Cyber Initiative, and we're a state program establishing Virginia as a global center for excellence in cybersecurity research. We support research, workforce development, and innovation at the intersection between cybersecurity, autonomous systems, and intelligence. And each year, CCI and CVN sponsor research and experiential learning projects. So today's speaker is a recipient of that funding. So today we have Dr. Yanxiao Zhao. And she is an accomplished associate professor in the Virginia Commonwealth University Department of Electrical and Computer Engineering, holding a Ph.D. from Old Dominion University. Dr. Zhao is a leading expert in wireless networking, IoT, and cybersecurity. And her research portfolio is extensive, covering areas like cybersecurity, wireless networks, energy harvesting for IoT, and smart grid communications. Her exceptional contributions have earned her recognition, including the Best Paper Award at 3 international conferences. Beyond her academic achievements, Dr. Zhao's research has secured several grants from different agencies like the NSF, NASA, the Air Force, and CCI, and her work plays a pivotal role in improving wireless network security. Dr. Zhao's insights on intelligence reflecting surfaces assisted wireless communications.
All right, thank you, Zara, for the very nice introduction. Okay, so good morning, everyone. Today I'll present intelligent reflecting surface assisted wireless communications. Since you already know my bio information, I'll skip this part. For today's talk, this is the outline for today's talk. So in the beginning, I'll introduce 6G and beyond applications, as well as requirements to implement these applications successfully. And then we'll move on to the topic of intelligent reflecting surface. What is intelligent reflecting surface, and what are their potential applications? Specifically, in today's talk, I'll mainly focus on 3 directions. The first one will look at the security and threats in ARS-aided wireless communication system. The second direction, I'll briefly talk about how to use angle of arrival estimation for ARS system so that ARS is able to distinguish the signal source. The third direction, I'll cover how to design machine learning-based ARS model and how to evaluate the vulnerability of adversarial machine learning attack for ARS system. Okay, at the end, I'll draw some conclusions. All right. So in recent decades, right, we have seen the rapid evolution of wireless communication networks and their wide applications in virtually every sector in our daily life, including autonomous system, smart city, intelligent transportation, and many other areas, right? To implement all these new applications, they also have diverse requirements. How to implement this? So we know some prior drivers in behind. For example, the driving trends includes not just high speed, spectrum energy efficiency, right? So they also have some other like emergence of smart surface. Also, we look at the convergence of communication, sensing, control, localization, computing, right? So here we know that's a long list. Here I just name a few, right? Okay, so how to eventually meet these requirements, how to implement the new applications successfully. So definitely they are calling novel and enabling technologies, right? And for 6G, we can treat this as the integration of a group of new, novel, exciting, enabling technologies. For example, recent years, we talk about the millimeter wave and terahertz communication, and we talk about communication with large intelligent service, and also the interface between computer and brain, and also energy also energy transfer and harvesting, right? And in today's talk, I'll mainly focus on this part, communication with large intelligent surface. For intelligent reflecting surface, sometimes we use different name, like a reconfigurable reflecting surface, intelligent surface. So in today's talk, I use the name IRS, intelligent reflecting surface. Okay, so what is intelligent reflecting surface, IRS? So actually, for ALS, it consists of a large number of reflecting surface elements. So here we can see there's an example of ALS, right? We can deploy ALS on the wall, on the ceiling, or even on buildings, right? So here give us an example. We have a large number reflecting element, many element here, right? Each element is able to reflect signal here to the receiver, right? Since we have a large number of reflecting elements, so it's able to reprogram the wireless communication environment. So there's a attractive benefit for ALS. So we can say, so ALS is able to reprogram and reconfigure so that it's able to improve the communication quality for the wireless communication environment. It also has the low cost, energy saving, and no interference to others. It has so many benefits. So that's why in recent years, we have seen many researchers are working on this exciting and innovative area. Okay, so here we can see if there's a blocking object, it blocks the direct communication between the source and the receiver. In that way, in the wireless communication environment, the communication fails. But if we have ALS is able to provide reflected link so that the communication is possible, right? We can, and another flexibility from ALS, so we can manipulate, we can control, we can reconfigure the phase shift from each reflecting element so that the reflected signal from ALS can be constructively or destructively added at the receiver, right? So we can program the environment as desired, as needed. Okay, on this slide, I briefly show the theory in behind for ALS system. So here I just show a very simple scenario, just one pair, transmitter, receiver, and this is the ALS. And overall, if there's no blocking objective, so here we consider line of sight communication, that's a direct line, right? Besides the direct line of sight communication, from each element, from each reflecting element, it reflects the signal from transmitter to receiver. Here, if we consider unreflecting elements, so in total it has unreflected paths. So at the receiver side, the overall received signal at the receiver, we integrate all these unreflected paths plus direct paths. So of course, we also consider noise. So eventually, we are able to derive what's the received signal at the receiver side. And after some calculation, we can calculate what's the achievable signal to noise ratio at the receiver side. This is the formula, right? From this formula, we can see we can adjust the phase shift from ALS so that we can further control signal to noise ratio. If we are able to control signal to noise ratio, we can further control the transmission rate. Okay, that's the theory for how ALS work. Okay, and we also mentioned ALS has many potential applications. On this slide, we summarize 4 user cases. So for the first one, So just now, actually, I already explained this, right? If there's a blocking objective, no direct communication between source and destination. In other words, we say, okay, if the user is at the dead zone, communication fails. But fortunately, we can deploy ARS somewhere so that the transmitter and the receiver is able to communicate where the reflected surface. Okay, this is the first user case. The second user case we consider, we can use ARS to improve the physical layer security. Now let's see the scenario. For example, we have legitimate transmitter, legitimate user, and there's eavesdropper, attacker there. The eavesdropper try to steal information from base station. In this case, since the eavesdropper is very close to the base station, if no ARS deployed, eavesdropper is able to steal information. In this case, what we can do, we can deploy ARS to cancel out the communication, the direct line communication. In that way, eavesdropper is not able to communicate with base station successfully. So we can prevent eavesdropping from the attacker. The third user case we consider, so if some user at the cell edge, the signal is very weak from its own base station. On the other hand, it also suffer the interference from another base station. In this case, what to do? Once again, we can deploy RS to improve the signal from its own base station. At the same time, we can attenuate the signal from the neighboring interfering base station. The last user case, we can also deploy ARS to form massive device-to-device communications simultaneously. For example, here we see many device-to-device communication. We can control the phase shift from reflecting surface to achieve the massive D2D communications. And in future, we expect more and more applications using ARS. For example, we may deploy this in a smart office, both indoor and outdoor. We can deploy ARS, for example, on the building walls, and we can implement this for smart transportation. So that's our expectation. We expect more and more applications using ARS. Definitely, ARS bring many benefits, but we also need to be aware ARS also raise some significant concerns from different perspectives. For example, the security issue, the performance optimization, signal differentiation, etc. And into this talk, I plan to cover all of this: security, performance optimization, and signal differentiation. The first part, let's look at the security and threats in ARS system. So for this part, we divide possible scenarios into 4 scenarios, A, B, C, D. For scenario A and B, we assume ARS is controlled by legitimate users. For scenario C and D, it's possible ARS can be also manipulated by attackers. So we'll look at 4 scenarios. The first scenario, let's see. Scenario A, look at scenario A. So in scenario A, ARS plan to protect legitimate user, receiver from eavesdropper. So here we can see that the eavesdropper, legitimate transmitter, and the receiver. So to prevent eavesdropping to the eve, what to do? We can let base station transmit a signal with a very low power so that eavesdropper is not able to hear the signal. At the same time, we can use ARS to enhance the signal strength by reflecting the signals. In this way, we can see the signal-to-noise ratio between legitimate user is increased, and the signal between base station and eavesdropper is pretty low. So in this case, we can protect legitimate receiver from eavesdropping. So scenario B, in scenario B, we see we have a pair of legitimate user transmitter. That's a legitimate user receiver, but there's a malicious attacker. Malicious attacker try to communicate with legitimate user. In this case, we would like to mitigate the attack from this attacker. Then what to do? So we can deploy ARS, right? That's a direct line. We can deploy ARS to cancel out the signal between attacker and receiver. So in this way, by deploying ARS, we are able to mitigate attack from attacker transmitter. In scenario C, we said before, ARS could be manipulated by attackers. In scenario C, there's eavesdropper there. So the eavesdropper can also control the ARS to improve the signal for himself or herself. So in this way, the eavesdropper is able to steal information from legitimate user. That's the adverse application of ARS. The last scenario D. So once again, here we have legitimate transmitter and the receiver. There's an ARS. Unfortunately, ARS is controlled by malicious users. So the malicious user can serve as a green jammer, try to interfere the normal regular communication between the legitimate pair. So in this case, ARS is deployed. So here we can see the ARS is controlled by malicious user to reflect the signal from the base station to the user destructively. Means the attacker use reflected signal to cancel out the direct communication between legitimate pair. So in this way, we can see attacker launch the jamming successfully. So just now we talk about 4 basic scenarios in terms of security concern for ARS. On one hand, ARS is able to improve communication performance for legitimate user. On the other hand, ARS could be controlled by attackers so that they can harm the normal communication. For simulation part, so just now we cover 4 basic scenarios, A, B, C, D. In terms simulation, we can actually divide all these 4 scenarios into 2 categories. The first category, in terms signal to noise ratio improvement. The second category, we look at the signal to noise ratio decrement. Okay, so here to run simulation, first we look at scenario A and C. Scenario A and C, they focus on signal improvement, either for legitimate user or for attacker. So to run simulation, so we use online the same RS channel modeling. So we deploy ARS at different locations and observe the relationship of ARS to signal to noise ratio. Okay, so here, for example, in this simulation scenario, this is the transmitter, blue, the star, that's the receiver. We deploy ARS at 2 different positions. This one position, this another position. Then we run simulation and try to observe the signal to noise ratio in terms of the power. We also look at different number of reflecting elements. So in this figure for ARS1, we consider no ARS situation. That's the red one. And then we consider the reflecting elements number is 16, 64 to 56. We can observe the simulation result, right? With ARS, we are able to improve signal to noise ratio by adjusting the appropriate phase shift. At location 2, we observe the similar trend. With LS, we are able to improve SNR. Further, if we continuously increase the number of reflecting elements, SNR is further improved, right? Okay, this for the signal to noise ratio improvement by LS. The second category, we look at SNR reduction by LS. The simulation results setting is very similar to the previous one. We put LS at different location and observe the signal to noise ratio impact. But this time, we adjust the phase shift to reduce the signal to noise ratio. The red color means no LS. With different number of reflecting surface, 16, 64, 256, we see we are able to reduce the signal to noise ratio. For location 2, they share the similar trend. Okay, so from simulations, we have shown that we are able to control signal to noise ratio by reconfiguring the phase shift of LS. Okay, this is the part 1. The second part, I'll focus on signal differentiation. So from the previous presentation in terms of security or some other recent work in LS, we have a very strong assumption. We assume the signal source is known. In other words, the LS understands, okay, which signal is good one, which signal comes from attackers, so that LS can do different actions, right? For example, should I improve the signal strength or should I reduce the signal strength, right? So there's the a challenge for LS system. So how to solve this challenge? How to let LS to identify the source of the received signal in practice. So we propose we can enable LS to distinguish signal from different sources by measuring their arrival angles. So we propose a hybrid LS architecture. Specifically, we have the green color represents passive reflecting element, the red one represents active element. So we propose hybrid LS architecture. It has both active and passive elements. For active elements, they have two working modes, spectrum sensing mode and reflecting mode. During spectrum sensing mode, they can serve as linear antenna array, so that it's able to distinguish signal by observing the arrival signals. So there's the theory part. So we consider it has D signal sources. For example, one is from legitimate, others are from unknown attackers or from unknown sources. So for each active reflecting element, it receives the signal, right? We can represent the received signal in this way. We consider all this D signal source and derive the formula for the received signal. Further, we represent the signal in the vector matrix, calculate the correlation matrix, and by using eigenvalue decomposition, we can form this as signal and noise, orthogonal signal and noise space. Then we apply music. Music is a very famous angle of arrival algorithm. So we use music spatial spectrum, and we can see if we use music, the peak only appear from the signal arrival direction, so that we can estimate what's the angle of incoming signal. If we already know the direction of the incoming angle of legitimate user, we just need to compare both. and conclude, okay, the signal is from legitimate user or from other unknown sources. So we use MATLAB to run simulations. So look at the first scenario. So we consider 5, 10, and 15 active sensing elements. For ARS, we can see different color represent different number of active reflecting elements. The red one, there's the 5. The black one, that's 10. And the blue color, that's the 15. So we consider 4 different signal sources. So here, that's the angle degree. 4 different sources. Now we can see by applying music AOA algorithm, it's able to detect the incoming degree accurately. Further, we see if we increase the active reflecting elements, for example, the blue one, we can see it has a best accuracy. Okay, so this simulation results show us the music is feasible. It works well if these 4 sources are separated far, right? Because they have different, look at here, 10 degrees, 20 degrees, -10, -20, by 10 degrees apart. The second scenario, we look at the detectable angle difference for the music AOA algorithm. So we try to make these 4 sources getting closer and closer to each other and see, is that possible for music AOA to detect the different angles? So here we consider 3. The red color, from the red color, we see that 1 degree apart. And for the black one, only half degree apart. This 1 degree apart. The blue one is 0.25 degree apart. Okay, now we can see when the signal sources are getting closer to each other. The red one looks fine, even though the resolution is not that high, but it's able to detect 4 different signal sources. For the black one, roughly that's fine, it's acceptable, right? We can see 4 peaks. For each peak represent each incoming signal source. But for the blue one, 4 signal sources are only 0.25 degree apart. There's no way for music to distinguish each other. Okay, so we know for the angle of Revel algorithm, it has limitation, right? There's one limitation if signal source are close to each other, or if they have the same angle, they are not able to detect different signal source. So that's the limitation for the angle of a Revel algorithm. So how to further improve the performance? We may not only look at, for example, we may not only look at the angle perspective. We also need to consider other factors. For example, the distance, right? If we look at both angle and the distance, this will give us a better picture about the signal source, different signal source. So this is the current work we are working on. Okay. The third part, so I would like to briefly talk about how to design machine learning based model to describe RS system. So nowadays we hear about machine learning is very powerful, right? Machine learning, AI, those are very popular and are used in almost all areas. Okay, so how to design machine learning model for ARS system? So my research team has been working on this. So we know for a large number reflecting surface, right? So we need to adjust each element. We need to adjust the phase shift for each element. We also need to consider when we have different locations of ARS. So make the ARS assisted communication system very complex. So for example, if we would like to achieve the optimal transmission rate, optimal signal-to-noise ratio at the receiver side. How should we adjust? How should we configure the phase shift of each element? This is a challenge. That's the problem. So we propose design machine learning model and try to optimize the ARS phase shift matrix. Okay. So specifically, we develop a hybrid ARS architecture. In part 2, for the AOA differentiation part, we already mentioned the hybrid ARS architecture, right? In hybrid ARS architecture, it consists of both active and passive reflecting element. So for the machine learning based model, so we can deploy a small number of active reflecting elements. Then for the active reflecting element, we can estimate the channel vector. Then we would like to predict the overall channel vector using the machine learning model. So that's the goal for this project here. So see, we have both passive and active elements. Then we develop machine learning model and try to derive, okay, what's the optimal phase shift? The optimal phase shift, for example, can reach the maximum transmission rate to maximum signal-to-noise ratio. Okay, so here I present some details. For example, the transmitter and the user, they send to orthogonal uplink pairs to the active elements. The active elements can estimate the palette signal and construct the environment descriptor. So we use the channel vector as the environment descriptor because it somehow show to represent what's the communication environment. So we use the channel vector from active elements serve as the environment descriptor and feed this to the machine learning model. And then we design the machine learning model to predict the optimal phase shift matrix for the overall ARS surface. Okay. So specifically, there's the four layer machine learning model. The input here, that's the environment descriptor I just explained. So we use a channel vector from active elements as environment descriptor. It has 4 layers. For each layer, the neurons, for example, 2M, 4M, 4M. M represent the reflecting elements from the surface. And the output here, that's a predicted optimal phase shift matrix, because we are looking for optimal phase shift matrix to achieve max transmission rate or to achieve max signal-to-noise ratio. Okay, then we run simulations to test the performance of the designed model. For simulations, we use a deep memo online data set. So we can generate different scenarios here. So we consider the outdoor scenario here. This base station transmitter, this the transmitter. Wait, let me see. Okay, this the transmitter here, and this the base station. This the ARS. Base station 3 serve as ARS. Then for the receiver, those are possible potential positions for the receiver. We consider over 54,000 candidate receiver locations for the training. So we use 80% for training, 15% for testing. Okay, and that's the scenario for our simulation. Then we compare the result. We compare the result from machine learning model and with the upper bound. For the upper bound, for example, here, the blue color, that's the upper bound. Upper bound means for the upper bound scenario, it has the perfect channel information. So that's the best result they can achieve. Then we use machine learning and try to compare the performance from machine learning and the upper bound. Now we can see if the data size is large enough, it approaches upper bound. For the blue color, we consider different element numbers. For example, we consider 32 by 32. For the red one, we consider 64 by 64. For both cases, we can see the performance from machine learning model is approaching upper bound. Means as long as we have enough data set, the machine learning model works pretty well. Okay, this is about machine learning based LS modeling. Just now we developed the machine learning model. The next question, we also need to be aware adversarial attack. Adversarial machine learning attack, they use different technology to manipulate or deceive machine learning models by introducing carefully crafted inputs. We call these inputs as adversarial examples. The goal of these adversarial examples or adversarial inputs, they try to cause misclassification from the model, undermining the integrity of the model, or even bring security for the machine learning model. So we have to be aware how to make our machine learning model robust against the adversarial attack. Okay, so followed by the designed machine learning model, we also evaluate the adversarial attack. They have different adversarial attacks technologies. For example, we consider 4 widely used attack models, such as a fast gradient sign method, basic iterative method, momentum iterative method, and projected gradient descent methods to generate adversarial examples and evaluate the vulnerability of the proposed model. Then later, after evaluation, we see our machine learning model is pretty weak against the adversarial attack, but we can further improve the robustness. We can use defensive distillation method to reduce the vulnerability against adversarial attack. So the following, I briefly present some work. So this work is work together with our collaborators. So for the left figure, right, those are undefined. We don't consider adversarial attack training. So we can see the MSE is pretty bad from all adversarial attacks. Then later we can train the model and improve the robustness. So now we can see it's getting better. This is the defined model. This is the defined model. This is the undefined model. We see it's getting better, but we also need to be aware, if the attack power is big enough, right? Machine learning model still at risk of adversarial attack. So this reminds us for future study, when we develop a machine learning model, we also need to keep in mind those machine learning models are probably vulnerable to adversarial machine learning model attacks. All right. Okay. Now I briefly present 3 directions. Let's have a quick summary for each direction. The first one, we cover the security and the threats using LS. We study the potential security impact of LS on wireless communication system. We cover 4 basic and typical scenario using LS for security or threats. And we also evaluate the LS performance in terms of signal-to-noise ratio improvement or reduction. The second part, we cover how to apply music angle of arrival for signal classification for ARS system. We know it's very important for ARS to distinguish the signal source so that it is able to further take different actions. So we borrow the music algorithm and show the effectiveness and also show the limitation of angle of arrival algorithm. The last part, I cover machine learning based LS model, and we develop a machine learning model, a deep learning model. Then later, we also evaluate the vulnerability against adversarial attacks. Okay, so that's all for today's talk. Thank you.
Thank you so much for sharing your presentation with us, and thank you everyone for coming. We really appreciate it. And stay tuned to our LinkedIn because we will be having another speaker next week. So yeah, we hope you guys can attend that one as well. Thank you so much.